you everyone for attending today's Foxconn Quantum Computing seminar. Today we have the pleasure of having Campbell McLauchlan, who will tell us about dynamical magic transitions in monitored Clifford+𝑇 circuits. So Campbell is a postdoc working at the Quantum Theory Group in Sydney. He obtained his PhD from Cambridge in 2024, working under Benjamin Berry on topics in quantum computing and many-body physics. In 2023-24, he gained experience working in quantum error correction at Riverlane as an intern and quantum scientist, and at UCL as a postdoc. And prior to the PhD, he has a Bachelor's of Science honors from Sydney and a Master's from the University of Cambridge. And his main research interests are in quantum error correction, quantum computing, and dynamical quantum phenomena. Campbell, the floor is yours.
All right, thank you. Okay, just to double check, you guys, you can all see this okay?
Yes.
Great. Are you also able to see my cursor?
Sort of switches from small to big size. I
Yeah,
guess
that's
it's
fine.
intentional.
Yeah, it's okay.
Okay.
Just I might use it to sort of illustrate things. But okay, firstly, yeah, thank you very much for having me and inviting me to give a talk here. I'm very pleased to be able to speak to you all. So this is some work that we published last year. This is done in collaboration with Mietje here, who's the lead author on this project, and Benjamin, who was my PhD supervisor, and this was work done while I was at Cambridge. I guess just okay, so sorry, this is the QR code linking to the archived version of the paper. Okay, so to dive into some context, this is kind of the main question that I want to use to sort of motivate this talk. So I'm thinking of quantum advantage. So when can quantum computers do something that classical computers can't do? I think this question is interesting from many perspectives, and particularly from this question, a sort of foundational perspective. So what are the ingredients that are needed for a quantum advantage? And of course, there's a practical perspective as well. So if we're wanting to build quantum computers, we better make sure that they are doing something useful. And so there are many ingredients that are required for quantum advantage. I'm just going to focus on a couple of them in this talk. And those are entanglement and magic. So, if a circuit sort of creates only a small amount of entanglement, then it's possible sometimes for a classical computer to easily simulate that circuit. And then similarly, this notion of magic is closely related to Clifford circuits. And so we know that Clifford circuits are also easy to simulate. So I'm going to get into this in more detail. But yeah, I guess, sorry, I also should point out that I've just made a little switch from thinking about like things that quantum computers can do better than classical computers. Of course, that's equivalent to saying, okay, what are the things that quantum computers can do that are easy to simulate by a classical computer? And that's kind of the perspective that I'm going to be running with in the talk. So I think that there's a sort of interesting perspective on this question, and of course I'm thinking about sort of quantum computing, but also I'm thinking of the systems that I'm going to be talking about as kind of modeling quantum dynamics. And so by talking about regions of these phase spaces that are easy to simulate, I kind of like to think of it as probing the boundary between sort of quantum and classical dynamics. And I guess the reason is that if you've got some dynamics that is easy to simulate, it's in some sense in this low complexity regime. It's not sort of exploring the full possible Hilbert space that it can explore. And so we sort of think about that in a it's a more kind of classical dynamics. It's not kind of fully quantum in this way. So I think this is also providing some motivation for looking at quantum advantage, and specifically quantum advantage in dynamical systems. We're sort of thinking of this as like as one of the ingredients that are required for these dynamics to be kind of properly quantum. And And so what I'm going to be doing is modeling these systems, so dynamical systems and also quantum computations in such a way that the resources that I mentioned before can be easily studied. And so to draw focus a little bit more, the type of model that I'm going to be looking at are random quantum circuits. So these are important for various reasons. So of course, a few years ago, or starting a few years ago and sort of continuing until today, there have been many experiments looking at quote unquote quantum supremacy. So these are sort of, for example, random circuits that are applied in real quantum computers. And the task of the quantum computer is to sample from the output distribution of this random circuit. And it's known that this is difficult, right? So, or difficult to classically simulate, I should say. So I think these random quantum circuits are interesting from this perspective of these like actual regions of or actual demonstrations of quantum advantage that can be seen in experiment. But they're also interesting for other reasons as well. In particular, they can be thought of as models for quantum chaotic dynamics. So this is this is the type of model that I'm going to be focusing on. And as I said, these are known to be hard to classically simulate. So this is why they might be interesting from the perspective that I've already talked about. But it's also known that certain mechanisms can destroy this hardness and trigger a transition to dynamics that are easy to simulate, and so sort of more classical in some sense. So what we want to do is we want to understand these mechanisms for transitioning from some hard to simulate dynamics to some easy to simulate dynamics, and thereby understand this sort of boundary between, well, it's sort of grandly speaking, the sort of quantum and classical world, with these two types of dynamics that differ in complexity. Okay, so that's the context. So just to outline the rest of the talk, so I'm going to spend a decent amount of time covering some background information. So hopefully that will bring all of us up to speed, which will be required for getting into the next section of the talk, where I'm going to introduce some key concepts that that motivate or that help explain some of our results and findings. And then I'm going to go into more detail on these findings in part C here. Okay, so just to jump off into background. So it was found, so as I said, we're going to be focusing on random quantum circuits, and there's a surprisingly rich array of physics on display in these systems. In particular, it was found a few years ago that if you consider one of these circuits, which is shown here, so in this illustration, what I've got are 2-qubit gates that are chosen randomly from some Haar measure, so just random unitaries on 2 qubits, and they're arranged in this brickwork pattern, and interspersed between these layers of gates are single qubit measurements. And each of these measurements is applied with probability p, which is some fixed probability. So in this kind of seemingly simple system, we have some pretty, I think, fascinating dynamics on display. So in this paper, what they looked at was the entanglement that's generated by this circuit. So what we can do is we can look at this entanglement entropy associated with a subregion A. So that's, yeah, okay, I've shown that here. So I'm just selecting out some subregion, and I can look at the von Neumann entropy of this reduced density matrix. And it turns out that there are two very distinct regions of this phase space. So for low enough p, it turns out that the dynamics generate a lot of entanglement. So that's this kind of red region shown here. Whereas for larger p, the dynamics generate only a small amount of entanglement. And so this is sort of illustrated here in a sort of cartoon way. And just to maybe go into a little bit more detail of what this means, so we call the large entangled phase the volume law phase. So what that means is that the entanglement entropy grows with the size of this region A that I'm selecting out. And in the low entanglement phase, I have what's called an area law entanglement entropy, where basically just this SA approaches a constant. So this is quite striking. It sort of makes sense in the sense that if I sort of add heaps of measurements to my circuit, those are going to break up the entanglement that's generated by the 2-qubit gates. But I think it was quite, it's quite interesting that this transition occurs at a sort of like, it's not some smooth interpolation between large entropy and small entropy. It's a sharp phase transition. And we can understand this as a phase transition in the ease of classically simulating this circuit, right? And the reason is that there are methods, these MPS methods, matrix product state methods, which sort of take advantage of the fact that there is only a small amount of entropy in the system to simulate the simulate the state efficiently. So in this weak monitoring phase, where we've got low probability and large entanglement, that's when the classical simulation is difficult, and then in this other phase, the simulation is easy. Okay. I'm going to switch gears and think about a slightly different perspective on this same system, and that's from an earlier paper, in fact. The difference is initially, in the previous slide, I didn't say this, but what I was considering is starting from a computational basis state input. Now I'm going to imagine what happens if I allow for this input state to be a fully mixed state. And so we still have some sort of competing dynamics. So what's happening is that these measurements are now going to try and purify this state, right? So they're going to try and project onto a pure state. Whereas the 2-qubit gates are going to frustrate the measurement's ability to do that. So what we can look at is this entropy of the entire state now, so the entire density matrix, which is obviously capturing some sense of purity of that density matrix, and see how that changes as we run this circuit. And so we can define a sort of characteristic timescale over which this entropy decays, tau p, and we can once again identify two phases. So in one phase we have the purification time, this characteristic timescale over which the entropy decays. This is going to be exponentially large in the size of the system, whereas in a different phase it's going to be only logarithmically growing in the size of the system. And what's kind of striking is that, or what's quite interesting, is that this transition directly coincides with the entropy transition that I just mentioned on the previous slide. So as I say, there's some very rich dynamics that that gets generated by this quite simple system, and it's very closely related to classical simulability. So this is just this is a figure from the paper, which is kind of just illustrating the point that I made. So I'm not going to dwell on that too much. So as I say, this is some perspective on the simulability of this system here, right? The simulability kind of via these MPS methods sharply transitions at the critical point. But that's just one notion of simulability. We also know that we have Clifford circuits, which are highly entangling, yet they're easy to classically simulate. So what I'm going to try and probe is some model where we can see a similar transition in the simulability, but from a perspective of stabilizer simulation and magic. So that's what I'm going to get into in just a second. But just to make sure that we're all kind of on the same page, I'm just going to very briefly review what are Clifford circuits and why are they easy to simulate. So I'm sure this is all kind of familiar with to many of you, but just to make sure that we're on the same page. So I'm going to be talking about stabilizer states a lot, and these are states that are in the +1 eigenspace of a collection of Pauli operators. And we're assuming that there are going to be n of these for n qubits. So, they fully specify the state. And I'm going to use this notation S brackets psi to indicate the stabilizer group that fixes psi. And that's going to be generated by these Pauli operators here. And the Clifford gates are those unitaries that preserve the Pauli group under conjugation. Now, the reason that stabilizer states are easy to simulate under Clifford evolution is that we can just keep track of these generators of the stabilizer group and how they get updated by the Clifford gates. Now, if we want to measure or if we want to sample from the output distribution on these stabilizer states, we can also do that efficiently. We can note that if a measurement commutes with all of the generators of the stabilizer group, then its outcome is deterministic. It's either plus or minus 1 with certainty. Or if it anti-commutes with one of these generators, the probability distribution is 50-50, so 50% probability of plus or minus 1. And we can also just easily update the stabilizer group to accommodate this measurement. Okay, so this is the Gottesman-Nil theorem. So I guess with that, I want to introduce the circuit model that I'm going to be considering. So this is going to look extremely similar to the previous case. We have these 2-qubit gates here, which are randomly chosen. Now, instead of them being Haar random unitaries, we're going to assume that these are random 2-qubit Clifford gates. And in order to sort of inject some magic or some non-stabilizerness into the system, we introduce these T gates, which are occurring with probability Q. And of course, these are non-Clifford gates. So these are going to be kind of controlling the hardness of simulating this circuit. Now, competing with these T gates, we still have these measurements that are occurring with probability P. These are going to be sort of aiding in simulation because they're going to be destroying the magic that's introduced by the T gates. Okay, so the simulation task is to sample from these the output distribution that's generated by these measurements that occur at the end of the circuit after some polynomial depth random circuit. Okay, and then of course, if this takes an exponential amount of time to simulate on a classical computer, we'll call that hard, and otherwise we'll call it easy to simulate. So just to jump right to the conclusion to begin with, what I'm going to be showing is that there exists a sharp transition in classical simulability via certain stabilizer simulation methods. And this coincides exactly, or it can coincide exactly with the entanglement transition that I introduced previously. So once again, on the sort of within the area law phase, it also is easy to simulate using these sort of stabilizer techniques, and in the volume law phase, it's hard to simulate using these techniques. But perhaps more interestingly, we can push this transition into either the volume law phase or the area law phase using a couple of different ideas. And so I guess the overall take home is that there is a sort of distinction between simulability transitions resulting from entanglement and resulting from magic, but that they can generically coincide as well. Okay, so just to that's where I'm heading, and now I'm going to sort of build up.
Sorry, Campbell, can I just interrupt briefly? Can you just elaborate a little bit on why there is a distinction? Like you're saying there is a distinction. What is that distinction, or why?
So I guess the distinction is that we could have we could have circuits which are easy to simulate via, say, MPS, but difficult to simulate via like these stabilizer simulation tasks. Or sorry, put it a different way. Easy to simulate via MPS. There's like a lot of there's not much entanglement, but there's a lot of magic in the system, and we can be in a distinct phase with either high entanglement, low magic, high magic, low entanglement, and so on. So as in this phase space has all of these regions that are accessible, but we do need to sort of tweak the model a little bit in order to see these.
Okay. Yeah. Thank you.
No worries. Are there any other questions at this point? Okay, cool. Okay, so I'm now going to get into some of the techniques that we're using to analyze this problem. And so the main tool that we're using is this technique of Pauli-based computation. So the idea here is that we're in this land of Clifford+𝑇 circuits, and what we can do is replace all of these T gates by a resource state, this magic state here, which is shown. And if we're allowed to, so if we create one of these resource states and apply a certain gadget to the target qubit and the resource state, we can inject a T gate acting on the target qubit. Now, this gadget here is probably looking extremely different from something you might have seen previously, but it's really the same as a T gadget you might be familiar with. Just to talk through it, so this is a joint measurement on both the target qubit and the ancilla, and this is a Clifford gate, which I don't need to sort of write out explicitly, but it's just some Clifford correction that kind of disentangles these two qubits once again. And then this is a Clifford correction, which is dependent on the outcome of this measurement here. Okay, and yeah, this is equivalent to just applying a T gate to the computational qubit. Okay, so the first step in PBC is we replace all of our T gates with these gadgets. And the reason that I've drawn the gadget in this way is so that the Clifford gate U is occurring after the measurement. The reason for that is because the next step is that we commute all of the Clifford gates to the end of the circuit. So once they've been commuted past all of these measurements, they can just be deleted, right? They no longer affect the output distribution that we're trying to simulate. Okay, so right, so then after that, we just have a bunch of measurements acting on our two registers. We just have the two registers, as a reminder, are this Rn. This is the initial n qubits that we started with, and then we have T ancillas in this register Rt, where little t is the number of T gates. And it turns out that you can actually sort of manipulate your circuit so that all of your measurements only act non-trivially on this register of magic states Rt, and the initial register you started with can actually just be thrown away. And moreover, all of these measurements mutually commute, and there are at most T of them that are independent. And importantly, all of these manipulations can be done in polynomial time. So the entire simulation task has been reduced to this simulation of measurements acting on the ancilla register. And then, okay, so we want to simulate these measurements. And so the way that we do this is we decompose this tensor product of T magic states into some hopefully relatively low rank, or not, well, the lowest possible rank decomposition into stabilizer states. And then we can simulate these measurements on these stabilizer states efficiently. Unfortunately, or maybe fortunately for quantum computing, this stabilizer rank is going to be exponential in the in T, so in the number of these ancilla states, and that's what makes this simulation difficult. But we've kind of turned this from something which was initially going to be exponentially difficult in N to now something which scales exponentially only in T. So if we only have a few T gates, this is a much better way of simulating things. Okay, and of course, in general, this is going to be hard. These measurements are going to be sort of potentially spanning all of these qubits, and we're going to be in a regime where we inject sort of order n T gates into the circuit, and so the entire system is the entire simulation is going to scale exponentially in n. But can this ever be made easy? So the answer is yes, and that's going to bring me to some of the key concepts that I'm going to mention now. So just diving directly into this question of can this ever be easy? So suppose that instead of these measurements that span all of these qubits, our measurements can be broken up into these regions, which only sort of act non-trivially on a small number of qubits. So like here, this measurement only acts on one qubit, this one acts on two qubits, and these blocks of measurements sort of don't overlap. So now this is going to be easy, right? I can simulate all of these in parallel, and I no longer need to decompose this entire tensor product of T magic states. I can just deal with sort of small groups of these magic states by themselves. So this is kind of the idea that we're going to be running with. We're going to break the entire set of measurements on this magic state register up into these blocks that have no measurements overlapping between the blocks. And then we're going to be sort of designing what we call this runtime proxy, which is only exponentially penalizing the size of these blocks. Okay, so this is a very, very crude kind of proxy for how long it would take a classical computer to simulate this series of measurements. So here, TIs are the sizes of these blocks, and we have this sum over the TIs with some sort of exponential penalization of the size of each TI. So this is what we're calling the runtime proxy, CPX, sort of standing for complexity of simulating this PBC. And we're going to be focusing on a kind of average of this CPX. It's a slightly complicated average, which is trying to capture the typical value of this CPX. So we take the log of CPX and normalize it to the size of the magic state register, and then we average that over all runs of this random quantum circuit. So what is this going to look like? Well, if for example, we only have one block, which is size t, then of course log of 2 to the t divided by t, that's going to be 1, or it's going to be a constant, let's say. And so this, what we'll call this simulability order parameter, is going to be constant. Meanwhile, if all of these TIs are, say, order 1, so this is this regime here, this simulability order parameter is going to drop to 0 because of this normalization. Okay, so these are the kind of two pictures to have in mind. We've got this hard regime where all the blocks are really large, and this easy regime where all the blocks are really small. And those two regimes are captured by this order parameter here, which we're going to be examining. And this sort of breaking up of these measurements into small blocks, we sort of term magic fragmentation, just to give it a name, I suppose. And the idea is that magic fragmentation is equivalent to PBC being easy to simulate. But now we want to find out, when does this fragmentation occur? Okay, so this brings me on to the next key concept. So this is so we'll call this concept stabilizer purification. And the idea here is that we may start with some magic state, and it undergoes some dynamics and some measurements, and we'll say that stabilizer purification occurs if these measurements project it down into a single stabilizer state. So it's kind of akin to purification that I talked about before, where we project onto a pure state. Okay, and this is going to be important for understanding what's happening. Excuse me. So let's go into a bit of an example. So suppose we have a stabilizer state psi, and we act on that with just a single T-gate, acting on qubit 1. So you can show that this stabilizer state acting on, being acted on by the T-gate can be written in this form here, where psi plus and psi minus are both stabilizer states, and their stabilizers are given, or their stabilizer groups are given here. So what's going on? So we first define the stabilizer of the state psi to be generated by S1 to Sn. And then we'll suppose, without loss of generality, that S1 anti-commutes with Z1, so the sort of Z acting on the qubit on which the T-gate is applied. And I say without loss of generality because if all of them commute, then the T-gate does nothing. So let's throw out that case for now and assume one of them anti-commutes, and we'll call that one S1. And then we can arrange the rest of our generators so that they all of the remaining generators commute with Z1. I can just multiply. Say if Sn anti-commutes with Z1, then I just multiply that by S1. to have an operator that commutes. And we'll call those new generators G2 to Gn. So all of these guys commute with Z1. And then the only difference between psi plus and psi minus is the sign of this Z1 stabilizer element. Okay, so there's kind of a nice way of thinking about this in terms of stabilizer codes. So we can imagine that what's happening here is that we're sort of creating a logical qubit encoded in a particular stabilizer code. So if you're not familiar with stabilizer codes, maybe don't worry too much, but if you are, then I think this is quite a nice way of thinking about things. And so the idea here is that we have a stabilizer group generated by G2 to Gn, and we have logical operators, which are S1, which remember had to commute with all G2 to Gn because of this stabilizer here, and Z1, which we also arranged to commute with all these generators here. And these two anti-commuted again by assumption. So okay, so these are logical operators that act on some qubit that's encoded in this stabilizer code here. And this logical qubit, as you can kind of see from here, is in a magic state. Okay, so now if I keep on applying Clifford gates and measurements to this state, it's kind of going to scramble this information into more and more non-local degrees of freedom. And so generically what's going to happen is that the supports of S1 and Z1 are going to grow. And particularly if we don't have measurements, if we just consider evolution under Clifford gates, these operators are going to spread, and the stabilizer code that's encoding this magic state is going to be updated. Okay. Now, the only way for a measurement to destroy that magic is for it to measure out the state of that logical qubit that I've created. So maybe that's intuitive, but we kind of go into, like, we explain that in a bit more detail in the paper. Now, there's going to be some, and we have this kind of light cone picture as well as to when this can occur. So you can kind of imagine this is a T gate, and we've got some light cone that's spreading out from this T gate, and a measurement has to be within this light cone in order to measure the logical qubit that's injected by this T gate. Now, it's not exactly the forward light cone from of this T gate. It's a little bit, it's a slightly larger light cone, which we call the causal cone of magic, but we're not going to worry too much about that. It's just to say that there's some sort of causality associated with when we can measure out this logical qubit. Okay. Now, the really key thing is that if we stabilize or purify, that is, if we measure out these logical qubits, so project onto a stabilizer state, that leads to the partitioning of the magic state register into these small size blocks. And so this is going to ultimately lead to some easiness of simulating the circuit. And so that's captured by this theorem here, which just states that the output of this circuit is going to be a stabilizer state if and only if the output of the Pauli-based computation is a stabilizer state. So let's kind of try and understand how this is going to work out in the big system that we're dealing with. So this is like cartoonishly illustrating the whole circuit. And what we're imagining is that at these times we stabilize or purify. So at this time we have a stabilizer state, then we undergo some more evolution, and this time we have a stabilizer state, and so on. And then in each of these blocks we introduce T gates. So sorry for the sort of reusing of T, but so we've got T1 T gates here, T2 T gates here, and so on. Okay, so then what? Using this theorem, we can kind of easily see that at this point here, if I look at the PBC that's produced from the circuit up to this point, the PBC is going to be in a stabilizer state, and it's going to look something like this, with measurements only acting on T1 magic states. And then if I run it for until the next SP event, I've got measurements only acting on T2 magic states, and so on. So if I'm stabilizer purifying often enough, then the magic states, the measurements on my magic state register are broken up into these non-overlapping small sets. So okay, this is now the flowchart that we're dealing with. if we regularly stabilize or purify, so that's we regularly project onto stabilizer states, that results in magic fragmentation, which, as I said, was the same as easily being able to simulate the Pauli-based computation. So, okay, there's a lot of sort of introduced jargon and stuff here, but maybe hopefully we can see where we're heading. Okay, so now I want to focus on what is the probability that this SP event occurs. And to deal with this in a bit of a simpler scenario, I'm just going to imagine that I only have a single T-gate again. And following this single T... Oh, yep, sorry, I have someone asking a question. Oh, sorry, I thought I heard I thought I heard something. Okay, yeah, just feel free to jump in at any time. Okay, so yes, as I say, we've got a single T-gate, and then following that T-gate, I've got a depth D circuit with no more T-gates, but with the random Cliffords and measurements occurring with the same probabilities that I introduced above in the way at the beginning. And then I want to find out what's the probability that this output state here is a stabilizer state. Now, yeah, I'm not going to go into all the details of this, but what I'm going to say is that this is where the connection to entanglement comes in. So this is, we make use of this second theorem here, which I guess I'll just give a little bit of a run through of, and then say that we can sort of use this to make an argument that make an argument about the probability of SP. Okay, so just to talk through this. So suppose I have a stabilizer group, which is generated by G1 to Gn, and I'm also going to define these destabilizers, Gi bar, and the way these are defined are just to be the operators, the Pauli operators that only commute, that only anti-commute with Gi and commute with all of the other Gjs. Okay, and then I'm going to consider a single qubit Pauli operator acting on qubit J, and I'll call that Mj. And this Mj can be expressed in terms of the generators of the stabilizer group and the destabilizers. And this is just because these operators kind of generate the Pauli group. And what I'm interested in is the number of these generators that I need in order to specify my operator here, in order to write down my operator here. And what we can show is that the number of these generators that I need, gamma j, is given by the von Neumann entropy of the stabilizer state stabilized by G. And this von Neumann entropy brackets J is saying, okay, imagine you partition your system at qubit J, sorry, you bipartition your system at qubit J, and look at the von Neumann entropy of half of that system. So, okay, this is a lot of words, but point is that if I have some large amount of entanglement, I need many stabilizer generators and destabilizers to write down my single qubit operator in terms of those stabilizers. Whereas if I only have a small amount of entanglement, I only need a small number of these. And so then...
Sorry. Can I just ask that why should we care about the number of generator we need?
Yeah, so it's a good question, and this is ultimately because we're going to use this, or we use this in the paper to argue that the probability of stabilizer purifying a particular state is either really large or really small, or sorry, I should say constant, or it's exponentially decreasing. So this just features in one of the arguments that we make. Does that make sense?
Can I also ask a follow-up question?
Yeah.
What is this partition again? Like, it seems a bit arbitrary. Is it just like, are you separating all the qubits above J from all the qubits below J or something? Is that how you're doing the partitioning?
Yeah, that's right. That's right.
And how does, I guess like the, ordering of qubits really matters when it comes to, entanglement stuff.
Yeah.
But it doesn't matter so much it doesn't matter at all when it comes to like stabilizer stuff. Can you just kind of comment on how this choice of partition is affecting anything?
Yeah, so it's a good question. So a lot of fine details are going to be kind of averaged out by the fact that we're just considering these random circuits. So like yeah, so I'm sure you could come up with specific examples when like you've got, I don't know, some super pathological thing with like no entanglement in each bipartition, but then I don't know, like heaps of bell pairs shared across the partition. I don't know if that really makes sense, but you know, I think you could come up with some pathological examples where, like, by reordering things, you can sort of significantly reduce this number gamma j here, but we sort of assume that those are going to be sufficiently rare as to not really be seen, and so that those don't kind of feature in the argument. Yeah, but so we sort of use this to allow us to make some guesses as to the probability of this SP event, and then based on that, we sort of argue that there's this that this transition occurs, which I'm going to get to, and then we sort of back that up with some numerics.
Okay, cool.
So,
thank you.
Yeah. Good. Yeah. Any other questions? Right. Cool. Okay, so I guess we've got these two phases that I mentioned right at the top, which is the area law phase and the volume law phase. And the difference was that in the volume law phase, the entropy across a cut in the system is going to be of order n, whereas in the area law phase, that entropy is going to be constant. And so the idea is that these logical operators these logical operators that kind of store the magic degree of freedom, those are going to remain quite localized in the area law phase and quite delocalized in the volume law phase. So they're going to spread into these non-local degrees of freedom. And then what we do is we say, okay, the probability of measuring out one of these logical qubits is basically the probability that as I measure the logical qubit, which basically means I can't have any of these destabilizers in the expression for the operator mj that I'm measuring on qubit j. That may not be super intuitive, but the idea is that, like, if I include some of these destabilizers, then all I'm doing is I'm updating the stabilizer group of this kind of dynamically generated stabilizer code, but I'm not measuring out that logical qubit. And so we use this to sort of argue for the form of the probability. And this is kind of the take home. So in the area law phase, because this gamma j is a constant, then we say that there's a constant probability of measuring this logical qubit out in each layer of circuit. Whereas in the volume law phase, there is some exponentially small probability of measuring the logical qubit in each layer. And that's just because of the number of combinations of stabilizers and destabilizers that could appear here being exponentially large. Okay, so all of that is to say that in the area law phase, we've got, you know, much higher probability of removing the magic that's introduced by a single T-gate than in the volume law phase. So we can quantify this again by some timescale over which the probability of this magic surviving decays, and this timescale is either exponentially large in the volume law phase, or it's constant in the area law phase. And this is really similar to the purification time that I mentioned right up the top, or in, you know, one of the earlier slides, where again, if I introduce a mixed state here, I can look at the timescale over which the purity increases. And this is, again, either exponential in the volume law phase or it's logarithmic in the area law phase. So we've got this like really close analogy between some stabilizer purification and like actual purification of a mixed state. And so this is ultimately our argument as to why in a particular regime the entanglement transition coincides with a magic transition. So just to fill out this flowchart a little bit more. So we're saying in the area law phase, what happens is that you get regular stabilizer purification events. And that's just because the lifetime of any T-gate or the lifetime of magic that's introduced by T-gate is very small. It's a constant. So you regularly stabilize or purify. That, if you recall, leads to this fragmentation of the measurements in the magic state register, and that's the same as easy simulation. Okay, so I'm now just going to kind of illustrate that with some of the numerics that we did for this paper. So what to be a little more precise, what I'm going to do is I'm going to fix this probability Q multiplied by the depth of the circuit to be a constant, to be order 1. And that might look a bit strange. Well, why not just fix Q to be a constant? But I guess just pointing out that by doing this, there are still order n T gates that are introduced throughout the entire circuit, and so that generically is going to be difficult to simulate. But we're in this situation where there is some fairly large average separation between T gates, and so that means that we can use this argument that we considered before, right? Because these regions are growing, and yet the time over which the magic introduced by this T gate survives is constant. We can say that, okay, there's going to be regular stabilizer purification, and we can use the argument that I mentioned before. Right, so this picture here of like a single T gate getting kind of killed off by the circuit is going to be applying within each of these regions. So this is what's being shown here, and I'm mostly just going to be talking about this figure here on the right. So what's happening? So this is the probability of measurements on the x-axis here. We're fixing this QD to be 10% for just arbitrarily. And then on the y-axis here, this is our kind of typical complexity of simulating the task normalized by the number of T gates. And what you can see is that, like, for low measurement probabilities, we've got really high complexity. So this is indicating some exponentially growing amount of time that it takes to simulate these measurements. And I guess importantly, as we increase the size of the system, this becomes closer and closer to 1. But we see this really clear phase transition behavior that's occurring at around 16%. And indeed, if you do a finite size scaling analysis, you see this data collapse, which is quite nice here. So what that's indicating is that this is that there is a phase transition that's occurring here. Right, and this is okay. So this is and this is importantly, this is consistent with the argument that we had before, that this transition should occur exactly at the entanglement transition. This PC is the same as you find if you look at the entanglement transition for a random Clifford circuit with measurements. So this is exactly the argument that we or supporting the argument that we made before, that the transitions should co-occur. But as I said before at the top, we can push this transition into either the volume law phase or the area law phase. So how do we do that? Well, we can just increase the number of T gates. So if we have a fixed Q being a constant, so now we've got like many more T gates, and the argument that we had before doesn't apply anymore. The reason is that there is some constant separation between each of these T gates in space-time. And so the magic is allowed to build up without being removed by the measurements. So we don't expect a transition like we had before below what's called the percolation threshold. So we have some argument as to why the upper bound for any of these transitions should be at around 48%, and this comes from a mapping to a percolation model, bond percolation model. So I can get into that more if I have time, but the point is that we don't see the same behavior, and so in this case, the entanglement transition is distinct from the magic transition. And so this is kind of shown here. It may look like we've got this precipitous drop again, but what you can see down here is that we no longer have this nice sort of finite size scaling and data collapse and all this sort of stuff you would expect from a transition. So down here, the complexity is still increasing as I grow my system size. It's a little hard to really properly definitively say, oh yeah, this is what's happening. And the reason is that there are like very significant finite size effects that we find for like, yeah, fairly reasonable parameter choices. But I think the take home is yeah, you don't see this nice transition that you did before. Okay, so what about pushing this transition into the area law phase? So this is kind of more interesting, I think, because now we have a regime which I suppose was previously thought to be difficult, but we can sort of create a part of our model, or yeah, we can create a model where it in fact is easy. So the way we do that is by correlating the T gates and the measurements. So we introduce this probability P plus for the probability of applying a measurement given that a T gate has just been applied on that qubit, and then P minus, which is probability of the measurement given that no T gate's been applied on that qubit in this layer. And then it's kind of nice to think, and then we can kind of quantify this sort of partial knowledge of where the T gates have occurred. And sort of nice to think about this in terms of like a game where maybe I give you a certain number of T gates, a certain number of measurements that you can scatter through your circuit. And I give you some, maybe some information about where T gates are, but maybe I'm lying with some probability or something like that. And your aim is to use those measurements to remove all of the magic from the circuit. And so this alpha quantifies your knowledge of where these T gates are. And so if alpha is equal to 0, you have absolutely no knowledge of the locations of these T gates, whereas this is kind of the maximum value of alpha, and that corresponds to perfect knowledge of where these T gates are. And if you have sufficient measurements, then you can arrange for these for the simulation to be easy by just measuring after each T gate is applied. And so kind of, I think it's quite cool that we see this, again, this nice transition as you increase the amount of knowledge that you have of the locations of T gates. So we've got this sort of quite separate phase transition, which is now controlled by alpha. But importantly, this can occur inside the volume law phase. So you've got lots of entanglement, but you can arrange for the simulation to be easy. So that's kind of it. So what I guess to conclude, so we've got this mechanism for a transition, and we can use this to show that at least for certain scenarios, there is a magic transition that occurs with entanglement, that co-occurs with entanglement. But this can be in general distinct from entanglement, like I showed before. And this is sort of a transition both in the classical simulability, but also in the sort of amount of magic that exists in the circuit and the degree to which this magic spreads through the circuit. And I didn't really talk about much about magic spreading, but that's an important part of this. And so yeah, and magic spreading is kind of leading to the difficulty of simulating this Pauli-based computation. Right, so we've got this model that's showing these quite distinct behaviors and kind of probing this classical to quantum transition in different ways. So I guess some outlook is we're wanting to, we'd be interested in finding some information about this phase transition, and some way of doing that is by mapping to a statistical mechanics model. Second question, I guess, is can we utilize these insights to improve algorithms for simulating quantum circuits? And then like seeing how general these results are. So considering maybe more realistic dynamical systems and and how magic spreading can play out in those different scenarios. And so this, just to, if you would like more details, we've got the paper here, and there are also some more details in my thesis, which don't appear in the paper. So thank you very much.
Right. Thank you very much for a very interesting and informative talk. Okay, so we have a few more minutes for questions. So if you have questions, please feel free to unmute and ask them now.
Sorry if you don't mind me kind of getting out of full screen mode so I can see you all now as well.
Yeah, sure. Yeah, no problem. Right. Okay, maybe I can just quickly ask something. So for the numerical simulations that you're showing, like where you try to show these transitions, so like you have like hundreds of qubits, and the depth of the circuit would be roughly linear in that, I guess?
Yeah, we set the depth to be linear. That's right. I don't remember exactly the depth that we chose, but it was I think it might have just been equal to n, but it might be just some constant fraction of constant multiple of n.
Okay. Any particular reason for these choices?
Making the simulation run in not a huge amount of time. Yeah. I think, and I think based on the arguments that we said before, if the results should be more pronounced for larger polynomials or like larger degree polynomials of n, and yeah, the reason is that the T gates just become more and more sparsely separated at that point. So if you can see this for linear depth, then any other greater depth should certainly follow for this particular choice of QD.
And I guess for like lower depth, then it will just make it easier to simulate, I guess.
Lower depth, yeah. I mean, if you go to really low depth, like logarithmic, that's I don't know. I think maybe there should be some interesting stuff that happens at that point. Yeah, because now your T gates are getting much more close together. I think it should still be, just off the top of my head, I think it should still be the case that you see this transition, but you're going to have some more finite size effects, I think, in the case of logarithmic depth anyway, because you're just closer to the initial and final time boundaries.
All right. Okay. I will let other people have questions.
Could I ask something? I'm curious about whether these results depend on like the connectivity of your circuit. So I think you considered like a 1D system. If you consider 2D or like, you know, all-to-all connections, like how would you expect the results to change?
Yeah, it's a good point. So I think it's a little difficult to say without really analyzing it carefully. But definitely you would expect it to change because the entanglement transitions in higher dimensional circuits are distinct from the 1D case. But I think, for example, in like 2D, I suspect that maybe with some particular choices of these parameters, I think it should still be the case that that you can find this magic transition that co-occurs with entanglement. Yeah. It's just then. I think it's again just going to be due to the sort of size of supports of these operators that carry the magic degrees of freedom.
I see. Thank you.
No worries.
All right. Okay. Do you
Yeah,
have
maybe
any-
one more
Mm.
question. So I'm still a bit confused on the transition of area law to volume law and the magic phase. So you're
Mhm.
saying that they what's the situation that they can co-occur and
So
and, yeah.
yeah, so if the so we've got this kind of asymmetry between measurements and T gates, where the measurement probability is a constant, whereas the T gate probability is kind of a constant times the inverse of the depth of the circuit. So the Q, the measurement, the T gate probability times the depth, we set that to be equal to a constant, and then you see this transition co-occurring. Whereas we initially, I mean, yeah, as may be kind of sensible, we initially set this to be Q equal to a constant, and we weren't able to see this transition, and so I think we understand better now why that is. But yeah, that's so it's in this case that we see the transitions co-occurring. Does that make sense, Eric? Or
Yeah. Sorry, can you remind me why it's D again? Sorry.
D is the depth of the circuit.
Depth.
Yeah, which is going to be I think it's here. Yeah, which is going to be polynomial in N.
Can I just follow up on that? So maybe you explained this and I didn't understand, but is it clear why they coincide in this regime where QD is 01?
Yeah, so it's due to the fact that you can work out the kind of expected region, or the expected size of region in which you only find a single T gate. And this region, yeah, sorry, I probably skimmed over this and didn't explain it particularly well, but yes, these regions, the size of this region grows with N. And so because each T gate has its magic removed in constant time, but it's in this region which is growing with N, then it's, each of these, like, that corresponds to measurements in the magic state register that don't overlap with one another. And so that's easy to simulate. There is some extra argument that's kind of required here, which I didn't really go into. It's not enough to like just say, okay, well, they're separated in time. It's also important that they can just be separated in space, and that's sufficient. And that has to do with this kind of light cone argument that I mentioned before.
Right. So it's like this phase transition is a geometric property that's happening, and that's why it's the same for the magic transition and the entanglement transition.
Yeah, it's because in like you retain some notion of locality in the area law phase, because all your generators of like the stabilizer group, for example, are local in one dimension. You lose that sense of locality in the volume law phase, and so all of that, like, yeah, and correspondingly, all of your magic simulation gets hard. Yeah.
Okay, cool. Thank you.
All right.
Thank you for your talk.
Oh, thanks very much for having me.
Yeah, I think we should probably end. But I actually have a quick question. So
yeah,
when you have this like random Cliffords like in the brickwork, so they are chosen independently?
That's right.
Right. But how do these results depend on that kind of like randomness? So now if they're random but correlated, do I still expect these results to go through? Or
so like maybe this gate is correlated with this gate in some way?
Yes, or sort of like that.
Yeah, that's really interesting. No, I didn't consider that at all. I suspect that you could arrange that correlation so that you can kind of, I don't know, somehow game it so that like I don't know, measurements have a harder time of destroying entanglement or something like this. But maybe you would then need to correlate with the measurements as well, or T gates. So yeah, I mean that sounds super interesting, but I'm not quite sure off the top of my head what you would expect.
Okay.